They started where everyone starts, the spacecraft itself. The radioisotope thermoelectric generators, RTGs, ran hot, and heat is momentum when it leaves in one direction more than another. The high-gain dish was a mirror to infrared light bleeding from the back. Could Pioneer be a lantern pushing itself backward with its own glow? They scoped the louvers that bled heat, the angles of the RTG booms, the slow drift in electrical power as plutonium softened across the years. If the push came from heat, it should fade as the RTGs cooled. Did the data fade? Hard to tell, thanks to noise floors and patchy arcs of tracking. Gas leaks had a moment in the sun. A leaking thruster could fake a tiny, constant push, but Pioneer spun like a gyroscope. Any off-center hiss would tickle the spin rate. That rate barely twitched. Software. They chase time standards, transponder quirks, the biases that creep in when you average what you want to see. They tore through ephemerides, asking if a Mies-modeled planet tug or an unnoticed Kuiper belt mass could steal a wobble from the signal. The gravity tweaks, moaned whispers, and cosmological musings were fun in the hallways but thin in the ledger. The sign was wrong here, the magnitude there, or the math choked on other tests. Meanwhile, the number kept coming back. 8.74 times 10m/s2, plus or minus a whisker, as if the void had texture. That persistence pulled people deeper. One researcher took home binders of telemetry and began to build a thermal model by hand, night after night. Emissivity tables, cable routings, paint aging under cosmic rays. Another wrote code to peel the Doppler drift from daily noise, trying different windows, different ways to weight the data, watching peaks and valleys even out into that familiar lean. Each pass sanded a little off the mystery, or revealed a new burr in the wood. What nobody knew, not really, was how far the effect stretched. The anomaly seemed to settle in beyond the giants, somewhere around 10 astronomical units, and then it just persisted. If it was heat, it should breathe with the spacecraft's slow cooling. If it was space itself pushing back dust, charged grains, the sun's magnetic field draping against the interstellar wind, then maybe it was telling us about a medium we'd priced at near zero. The expectation at the time, once you clear the major sources of radiation pressure and leave the planets behind, gravity becomes simple again. The reality hinted that the solar system's edge is a layered place, not a cliff. Subtle pressures, magnetic tension, a fog you only feel when you try to move through it. Inside the lab, the arguments didn't break friendships, but they did harden positions. The navigation team trusted their tools. The thermal folks wanted every watt accounted for. The plasma crowd smirked at the word empty. Yet when the residuals went up on the screen, everyone leaned forward the same way. Because if the hand on Pioneer's shoulder was Pioneer's own heat, then something in the dark was putting that hand there. To understand why this headache was earned the moment the rockets lit, you have to go back to how these craft were built and why their very simplicity made their ghosts louder. That's where the promise began, and where the trouble found a clean stage. Pioneers built for forever. They were built like lighthouses that could drift. Spin kept them honest, no jittery reaction wheels, no constant fussing with attitude. Lock the high-gain dish on Earth, set the spin around the long axis, and let inertia do the housekeeping. Out on the booms, 4 radioisotope thermoelectric generators glowed steady, turning plutonium heat into a quiet stream of watts. No solar panels to angle, no batteries to baby in shadow. Just a hard, simple rhythm meant to last longer than anyone's budget forecast. That simplicity wasn't an accident. The teams wanted a platform that wouldn't hide its own sins. Fewer moving parts meant fewer unknown torques. Constant heat sources meant you could, in theory, account for every escaping photon. The big aluminum umbrella of the dish gave Earth a bright target to ping, and the S-band transponder sent back a tone so clean you could measure a change smaller than a mosquito's mass turned into speed. Everything about the design said, if anything nudges me, you'll see it. The irony is, that promise cuts both ways. A quiet machine makes its whispers loud. Spin stabilization smooths out the jitters, but it also hard bakes asymmetries. If one side of the bus throws off a little more heat than the other, the spin averages the direction but not the bias. The high-gain dish becomes a reflector for that warmth bleeding from the back, and a reflector doesn't care about your budget. It cares about geometry. A few stray watts favoring the forward hemisphere adds up to momentum, day after day, year after year. Engineers knew this in the abstract. They still chose the architecture because the trade was worth it. With no big fuel sloshing, no flexing wings, pioneers offered navigation teams the holy grail, a stable radio target that wouldn't invent phantom forces just because a hinge got sticky. The craft were also compact, antennas, booms, a hexagonal bus with thermal louvers that opened and closed like eyelids as the inside warmed and cooled. The louvers faced sideways, not aft. That mattered later, when people tried to draw the path of every stray infrared photon in a three-dimensional maze of hardware. The dream's simple: get past Jupiter and Saturn, slip through the orbits of Uranus and Neptune without stopping to chat, leave the bustle of sunlight where pressure still matters, and keep going until the sun's voice became a murmur. The spacecraft carried plaques with arrows and hydrogen atoms, but the deeper message was in the trajectory itself. This is how far we can make our math true. They didn't expect that true would pick a fight over heat, but even simple machines accumulate fingerprints. Paint ages under radiation. Multi-layer insulation sags, gets micrometeoroid pinpricks, changes emissivity by a few percent. Power falls as the plutonium decays, so heaters cycle differently. Cables aren't perfect. They conduct warmth like little roads, not like an Eden fog. Put those together and you've built a subtle bias factory. Nothing dramatic. No puff of gas, no thruster that forgot to shut up. Just a glow that prefers one direction. Here's the twist. The very things that helped navigation, the clean radio tone, the steadiness, also kept the environment out of the suspect pool longer. When your attitude is rock solid and your spin is steady, you look at the cosmos first. Radiation pressure from sunlight, drag from dust, magnetic fields tugging charged grains in the spacecraft's charged skin. But sunlight fades as one over the square of distance, and out where Pioneer lived, that pressure was a gnat. Dust. The cross-section was tiny, the densities implausibly low for a constant effect. Charged grains. Maybe, but spin would average many of those kicks. The outside got ruled out faster because the inside was designed to be quiet. And yet the platform had a second gift. It turned deep space into a calibration chamber. With every planetary flyby in the rearview, the only big forces left were gravity, thermal recoil, and whatever the local medium might be doing. If you could pin two of those, the third would have to show its hand. That's why engineers took such pride in balanced booms and fixed geometry. Pioneers weren't sent to do plasma physics on the way out. They were sent to not lie about the trip. They also weren't supposed to last as long as they did. Built for forever was a joke whispered with crossed fingers, but the hardware kept humming. The power faded predictably. The temperature curves wrote long, slow arcs. Those arcs let people test ideas years later that nobody budgeted staff for. A graduate student could take telemetry from the 1970s and map a thermal profile to a Doppler drift from the 1990s. A postdoc could ask if the louver open-close cycles lined up with wiggles in the residuals. The design, by being old-fashioned and sturdy, left breadcrumbs. And that leads to the deeper stake. When a machine is this simple, you can, in principle, account for each watt. You can draw a line from heat to motion and know what portion of the blue shift is just your lantern pushing off its own light. If there's anything left after that accounting, then it's not your lantern. It's the sea you built it to sail. The pioneers' very cleanliness made that test possible and made any leftover hum impossible to ignore. Out beyond the planets, the solar system thins. But thin isn't empty, and a clean ship makes whatever out there easier to feel. As the trajectory stretched into the heliosphere's outskirts, that wager, the one baked into every bracket and louver, was about to be called. Where empty isn't empty. Out past the bright tyranny of sunlight, we thought the road got simple. Gravity keeps score, photons fall away, and the medium between stars fades to a rumor. That was the story we liked. But the sun doesn't just shine, it breathes. It throws a wind, charged particles, magnetic fields braided into a helical stream that inflates a bubble around us. That bubble has a shape, a texture, and a temper. Empty turns out to be layers stacked on layers. Start with the heliosphere. Think of it as the sun's weather pushing outward until the galaxy pushes back. Close in, the solar wind coasts fast and hot. Farther out, it feels the weight of interstellar gas and the friction of tangled fields. There's a point where the wind slows from supersonic to subsonic, the termination shock. Beyond that, the heliosheath, the churning zone where slowed solar wind, magnetic tension, and incoming interstellar whispers mix like two oceans meeting. And farther still, the heliopause, the not-quite skin where the sun's breath finally yields to the interstellar medium. None of that is a cliff, it's gradations. But to a traveler measuring tiny forces with a radio tone, gradations can feel like edges. Subtle pressures that change slowly can masquerade as constants if your clock is coarse and your path is long. That's the trap Pioneer sailed into. The expectation baked into early navigation was tidy. After the planets, radiation pressure drops as 1 over the square of distance. Dust is scarce, and magnetic fields, while real, aren't supposed to hand out a steady push aligned with the sun. Gravity should dominate, predictable and clean. Reality had more knobs. The heliosheath isn't still, it breathes with the solar cycle. When the sun's activity swells, its wind stiffens. When it quiets, the bubble relaxes. Magnetic field lines drape and pinch. Charged grains skate along those lines. Neutral atoms swap charges with ions and slip through like ghosts, only to light up in ultraviolet when sunlight scatters off them. Dust counts rise and fall with filaments of the local cloud. Each ingredient is weak, but weakness over billions of kilometers can add up to a whisper you can hear, if your ship is quiet enough. Could that whisper look like drag? If there's a density gradient, a slow pileup of neutral hydrogen where the sun's force loses to the galaxy's flow, you'd expect a faint resistance, not a brick wall. Think more like swimming than crashing. The pushback would carry memory, responding to how the bubble swelled months ago, not just how it is now. To navigators squeezing meaning from Doppler shifts, that kind of resistance with history is a nightmare. It looks almost constant on short baselines and only reveals its heartbeat when you stitch many seasons together. Dust got its day in court. The cross-section of Pioneer was small, and interplanetary dust densities plummet with distance. Simple math said no. But then nanograins enter the chat, tiny charged particles that don't move like rocks, they dance to magnetic fields. Their effective drag isn't just mass hitting area. It's coupling, the spacecraft's own charge, the field geometry, the spin that averages kicks but doesn't erase a bias if the field prefers one direction. You can argue the numbers either way because the environment isn't uniform. It's veined like wood. Magnetic pressure wasn't supposed to matter for a lump of aluminum. The craft isn't a sail, but fields don't need sails to store stress. Where the solar field buckles against the interstellar field, tension builds, a kind of elastic skin. Flow tries to slip around, the skin stretches and snaps back, shedding waves and hums. If your craft drifts through a region where that tension is consistently higher on the sunward side, you feel a nudge. Not much. Enough to write a slope on a patient engineer's plot. And then there's the hydrogen wall, a phrase that would sound like science fiction if not for later instruments catching its glow. Picture neutral hydrogen atoms in the interstellar wind meeting the sun's outward flow. They can't come all the way unbothered. They pile up, just a little, where pressures balance. Sunlight scatters off them at a specific ultraviolet wavelength, Lyman-alpha. Decades after Pioneer whispered about drag, Voyager saw hints of that pileup in sky background. Years after that, New Horizons' ALICE spectrometer reported a persistent Lyman-alpha brightness that didn't fade with distance the way simple models predicted. Best explanation: an added, roughly constant component, consistent with a denser hydrogen layer near the heliopause. Wall isn't a fence. It's a slow build, bright enough to see, soft enough to swim through. All of this lives in the margins where navigation hates to live. The math prefers empty because empty stays put. A medium with memory shifts the ground under your feet. That's why, in the lab, the spreadsheets multiplied. If empty isn't empty, you have to price in pressures you don't measure directly, in places you don't yet inhabit. You estimate. You argue. You build models with knobs you promise not to tune more than once. And while you do, the clean ship keeps sending back that honest, infuriating line that leans. So when the data said drag and the models said no way, it wasn't just a fight about a number. It was a fight about whether our bubble has weather. The edge of the solar system isn't a vacuum you cross, it's a coastline. And coasts have surf, undertow, and long, slow swells you only notice after you've been in the water a while. The audit that ate a decade. They called it data archaeology for a reason. The story wasn't neatly filed on a server. It was scattered across tape reels, printouts, orphaned file formats, and engineering logs typed by people who'd long since retired. To chase a force you couldn't see, you had to rebuild the world that produced the numbers. So they started digging. First came the Doppler. Those blue-leaning heartbeats lived on aging magnetic tapes. Some weren't labeled cleanly. Some had timestamps that drifted by fractions of a second, enough to fake motion if you weren't careful. Teams wrote software to read extinct formats, compared playback heads, cross-checked station clocks. A week would vanish just aligning two arcs of data so they could sit in the same sentence. When the line still leaned, nobody cheered. They took a breath and kept going. Telemetry was next, the slow, patient record of the spacecraft's body language. Bus voltages, louver states, temperatures at awkward corners of the hexagon. You couldn't model heat without knowing how hot things actually were, hour by hour, year by year. But even telemetry has ghosts. A thermistor drifts. A sensor saturates. Calibrations get lost in a move. One researcher spent months tracking a single temperature channel back to a bench test in the 1970s, just to rescue a conversion curve from a photocopied binder. That wind shaved a sliver off the uncertainty. You could feel the force field of excuses shrinking. Meanwhile, arguments sharpened into homework. If this was heat, prove it with a model that earns its keep. Not a hand wave. A map of where every watt goes. Enter the heat model wars. Pioneers threw off thousands of watts as waste heat across their lives, mostly from the RTGs on those long booms. Most of that infrared left in all directions, but mostly isn't navigation. If a few dozen watts favored the forward hemisphere, bouncing off the back of the high-gain dish, sneaking past the bus insulation at an angle, that bias could look like a tiny steady push sunward. So they built a ship inside a computer. Facets, emissivities, cable routings as thermal highways. They fed the model real telemetry, RTG decay curves, power subsystem trends, louver open-close histories. They ray-traced photons from hot surfaces to cold ones, counted reflections, let the spin smear out direction but preserve bias. They made peace with dust on surfaces, paint aging under radiation, the small ugliness of real hardware. Then they asked the only question that matters. Does the recoil from this asymmetric light push add up to about 8.74 times 10 meters per second squared, with the right sign and the right time behavior? It's blurred. Microstory. A postdoc, eyes sandpapered, tweaks the emissivity of a cable bundle by 0.5% and watches the integrated recoil curve nudge closer to the Doppler slope. Another night it overshoots when he moves a virtual louver. He puts it back, curses quietly, and leaves a note for morning. Across town, a colleague refuses to touch parameters without telemetry backing. No tune by feel, she writes on a whiteboard. The room nods. If a model can match anything, it means nothing. Outside these rooms, the dogma of navigation was on trial. Do you trust the ephemerides, the polished tables of where planets and the sun should put you, or the telemetry that says your own ship is shoving itself? The quiet truth: you need both. Ephemerides anchor the garden. Telemetry tells you how hard your hose is pushing back. There were detours. Gas leak ghosts were cornered with spin rate histories. If a thruster whispered, the spin would stutter. It didn't, not in the way you'd need. Software biases were hunted with independent pipelines. Two teams ran the same arcs with different code and got the same blue drift. Cosmological daydreams, maybe expansion shows up as a local tick, fell apart under orders of magnitude and cleaner tests elsewhere. Each suspect that died made the heat case look less like a patch and more like a ledger. By 2012, Slava Turyshev and collaborators laid out a paper that read like a confession written by the spacecraft itself. Using telemetry-driven thermal models, they showed that asymmetric thermal radiation, RTG heat reflecting off the back of the high-gain antenna, plus warm electronics bleeding preferentially in the fore-aft geometry, could account for most, and in their analysis essentially all, of the observed sunward acceleration. Quote the line that mattered. Once the thermal recoil force is properly accounted for, no anomalous acceleration remains. It wasn't a mic drop so much as a long exhale. In the plots, the constant, 8.74 times 10 m/s2 softened into a curve that declined as the RTGs cooled, just as a lantern shove should. Not perfectly smooth, because telemetry is lumpy and the environment breathes, but close enough that the clean, flat hand on the shoulder started to look like your own shadow. Still, even believers in the thermal recoil story kept a drawer labeled residuals, little seasonal wiggles, hints of correlation with the solar cycle's pulse. Nothing you'd bet a career on, but nothing you'd throw away if you care about the edge as a living place. The audit didn't prove the cosmos was empty. It proved your instrument was louder than you thought, and honest enough to let you subtract yourself. While those models ground their teeth, another thread was unfurling far from the spreadsheets. A different pair of spacecraft were listening for the sun's border, not in Doppler slopes, but in shocks, plasma tones, and a faint ultraviolet glow. And when those ears
Voyager
brushed
touches
the edge, empty got a new
While
name. The Pioneer debate simmered under fluorescent lights, two older travelers were quietly steering into the weather. Voyager 1 and Voyager 2 weren't built to solve a navigation riddle. They were built to go sightseeing and then keep going. Decades in, their instruments were tired, some deaf, some half-blind. But a few could still feel the medium. That turned out to be enough. Voyager 1 felt it first. In 2004, Voyager 1 crossed the termination shock, the place where the solar wind hits a wall of reality and drops from supersonic to subsonic. The craft didn't see a line. It felt a change in the way particles smacked its detectors. The reading said the wind was slowing, the density rising, the magnetic field lines tangling. It had entered the Heliopause, the stirred-up zone where the sun's breath wrestles with the galaxy's current. Voyager 2 followed in 2007, crossing the termination shock at a different distance, which told everyone the boundary wasn't a neat sphere. The bubble was lopsided, pushed around by the local interstellar field and the sun's own uneven output. The two craft became a stereo pair, their separations turning the edge into a three-dimensional rumor you could start to map. Then came the plasma music. Voyager 1's plasma instrument had failed years earlier, so when 2012 arrived, the team had to get clever. They listened instead to plasma oscillations, the eerie hum that happens when a burst, like a solar outburst, rings the electrons in the medium. The pitch tells you density. All at once, the pitch jumped. The density they inferred matched interstellar space, not the Heliopause. That was the line. Voyager 1 had slipped across the Heliopause into interstellar plasma, still feeling the sun's field but drifting in a different sea. In 2018, Voyager 2 confirmed the story with its working plasma instrument, registering a clean density increase and a shift in particle populations as it crossed. Two independent travelers, two crossings, same song, different verses. What stood out wasn't a brick impact. It was a layered, sticky transition. Energetic particles trapped inside the bubble dipped. Galactic cosmic rays from the outside rose. The magnetic field direction shifted subtly. The crossings weren't simple. They came with spikes, plateaus, even brief retreats that looked like the craft were surfing corrugations in the skin. A wall didn't act like a wall. It acted like a boundary with memory and structure, a place where the sun's last words tangled with the galaxy's first. Here, where the Pioneer whisper met a new kind of evidence. Long before the Voyagers crossed, their ultraviolet spectrometers had measured a faint sky brightness at Lyman-alpha, the wavelength neutral hydrogen loves. The numbers were odd, brighter than simple models of sunlight scattering off interplanetary hydrogen would allow. People argued about it, said maybe there's a distant background, maybe calibration. Then New Horizons entered the outer system with an ultraviolet spectrograph named Alice and started scanning the sky. Alice kept seeing a glow in Lyman-alpha that didn't fade the way it should with distance from the sun. It held a roughly constant component, about what you'd get if there were a denser layer of neutral hydrogen near the Heliopause scattering sunlight back toward us. It wasn't a photograph of a wall, it was a fingerprint. The interpretation the team published: a hydrogen wall, a pileup where the outward solar wind pressure loses to the incoming interstellar flow. Not a fence you bounce off, but a drift line where stuff gathers, brightening the ultraviolet sky. The Voyagers' old hints looked less like quirks and more like first glances. 3 missions, spaced by decades, all telling a version of the same story. Now line that up with how a traveler feels the edge. If you swim through a region where density creeps up and magnetic tension tightens, you don't get a clean hit. You get resistance with memory. The particle populations around you carry yesterday's weather. Fields drape and snap. A spacecraft senses that as changes in particle counts, wave activity, and field strength, not as a neat, constant push in one direction. That's the difference between Pioneer's abstract slope and Voyager's lived environment. Pioneer read the medium through Doppler. Voyager wore it on its skin. So why did Pioneer's numbers look so steady for so long? Part of it is how you measure. Vectors of force, when smeared by a spinning, slowly cooling lantern, can integrate into something that looks flat if your time bins are wide and your noise tall. Part is where Pioneer was, well inside the Heliopause years before the Voyagers reached it, in regions where gradients change slowly across dozens of astronomical units. A swimmer in a lazy river feels drag without seeing the eddy that causes it. Human moment. When Voyager 1's plasma wave team first plotted that sudden pitch change, someone in the room said, "That's it." Not a shout, just a breath. They were hearing the edge rather than seeing it. Later, when New Horizons' Alice team overlaid their sky maps and that stubborn brightness refused to fade, there was the same quiet nod. Different instruments, different senses, same boundary. The wall, then, is real, but not a wall the way roads end. It's a rise, a sheath, a skin that thickens and thins with the sun's mood and the galaxy's tug. You don't crash into it. You pass through it, and it leaves fingerprints on your instruments. And that brings us back to the puzzle that started under fluorescent lights. If the edge resists like a memory foam more than a metal plate, what turned Pioneer's hum into such a tidy number? That question would press the community back into the math, to ask if constant was ever really constant at all.